In this presentation, I provide a brief introduction to exploratory factor analysis. In applied research, there are three approaches often described by researchers as factor analytic techniques: principal components analysis, exploratory factor analysis, and confirmatory factor analysis. While EFA and CFA are truly approaches for factor analysis, principal components analysis is not. PCA appears similar to EFA and CFA on the surface, but the distinctions are not superficial. Similarly, the distinctions between EFA and CFA are also quite important. Each of these three methods has a distinct purpose, and each is often used in the development of new instruments. While PCA, EFA, and CFA are three distinct analytic methods, they are also complementary methods that can be used together to strengthen research instruments and outcomes. This presentation is an introduction to exploratory factor analysis. Exploratory factor analysis, or EFA for short, is an analytic method used for the development of psychometrically sound measurement instruments. Suppose you're interested in measuring the extent to which someone might be swayed by social influences. Unable to find an existing instrument, you decide to create your own. You create a construct map and write many items that might help you measure social influence. The questions you write will correspond to the construct map, but their specific content will be based on your theoretical knowledge of the construct, that is, what you know from previous research. When you write a lot of items, you end up with a lot of data that can be difficult to interpret. This is where EFA comes into play. The extent to which responses of items vary together is called covariance. We can create a matrix of covariances of items just like we would create a matrix of correlations. The goal of EFA is to identify the groups of items that, when considered together, explain as much of the observed covariance as possible. Each of these groups of items is called a factor. EFA helps us to find meaningful patterns by identifying items for which responses seem to clump together or vary in a predictable way. It's up to the researcher to think about the content of the items in each group to determine what it is that those items have in common from a theoretical and conceptual perspective. Using factors instead of items makes analysis and interpretation simpler because it allows the researcher to work with a simpler, more parsimonious presentation of the data in which each aspect of a construct is represented by a single score instead of individual responses to multiple items. EFA is an exploratory descriptive approach. This means that it can identify many different factor solutions for a data set, but some of those solutions may not make sense theoretically. It also means there is no statistical way to know if the extracted factors are correct or not. These decisions are up to the researcher. EFA identifies factors, but the researcher must decide which ones make sense for the construct of interest. One of the guiding tenets of science is parsimony. This means that, as scientists, we should always look for the simplest way to explain and present information. Within the context of EFA, this means we want to identify the fewest number of factors necessary to explain the maximum amount of covariation among the item responses as possible. The EFA process consists of three distinct steps: extraction, rotation, and interpretation. When we conduct an EFA, the software will extract the same number of factors as there are items included in the analysis. The researcher must decide the appropriate number of factors to retain and interpret. The most common ways to do this are to review the eigenvalues associated with each factor and the scree plot for the overall analysis. When we conduct an EFA, we get values called factor loadings that describe the relationship between each item and each extracted factor. Factor loadings communicate how much of the variance observed within the variable can be attributed to the factor. Factor loadings have relative value, meaning that higher factor loadings indicate stronger relationships between items and factors. When we describe the magnitude of the relationships between items and factors, we talk about their loadings. To describe the magnitude of a factor, we talk about its eigenvalue. A factor's eigenvalue is the sum of the squared factor loadings for that factor. So if 5 items appear to load on a single factor, we would square the loading of each factor and then sum the squared values, and that would give us the eigenvalue for that factor. As a general rule of thumb, we begin our initial review of extracted factors by considering only factors with eigenvalues greater than or equal to 1.0. This is sort of an arbitrary rule, but it gives us a good starting point. Because our goal is to explain as much of the variation in responses as possible with as few factors as possible, we're better off with fewer factors that each have larger eigenvalues. Keep in mind that ultimately the factor solution we choose should make sense from a theoretical and conceptual standpoint. The theoretical and conceptual understanding is more important than the statistical understanding, but we can use statistics to verify our understanding of the theory and to improve upon the questions we ask in order to measure concepts related to that theory correctly. In addition to, or instead of considering eigenvalues, we can begin deciding how many of the extracted factors to retain by inspecting the scree plot. When we evaluate eigenvalues directly, we're considering their absolute size and comparing that size to a cutoff value such as 1.0. When we evaluate a scree plot, we are actually considering the relative sizes of the eigenvalues instead of their absolute size and whether they meet that specific criterion. To determine the best number of factors to retain using a scree plot, we plot two lines, one that fits the vertical shape of the plot and one that fits the horizontal shape of the plot. The point where these two lines cross is called the elbow of the plot. We then begin consideration of the extracted factors by thinking about only those factors that fall to the left of the elbow. In this example, we would begin our investigation by considering the first 6 factors that have been extracted. EFA offers a feature called rotation to help the researcher to better understand the relationships between items and factors, as well as the relationships between factors by changing the perspective from which data are viewed. Imagine the data points exist in a 3-dimensional space. All a rotation does is rotate that 3-dimensional space to allow us to take on a new perspective, or see things from a different angle. This is analogous to spinning a globe so that we can see the map of the world from different angles. In doing this, the factor loadings for each item become larger for the factor that it best measures and smaller for the other factors in the solution. We're not changing data values or the relationships between data points, we're simply looking at the information from a different angle. The decision to rotate or not to rotate a factor solution depends on the number of factors extracted and the extent to which each item loads on just one or more than one different factor. If we extract 2 or more factors and items load onto more than one factor with a loading greater than 0.3, we may choose to rotate the solution to change the perspective from which we view the data and the relationships with the factors. The type of rotation we use depends on whether the multiple factors are theoretically correlated with each other or not. If the multiple factors should correlate with each other, we would use an oblique rotation. If the multiple factors should not correlate with each other, we would use an orthogonal rotation. The specific rotation technique we use once we determine whether to use an orthogonal or oblique rotation is often a matter of trial and error. It's not unusual to try more than one rotation within a family to see which approach makes the factors most interpretable and consistent with the theoretical construct of interest. The final step in the EFA process is that of interpretation. This step is exactly what it sounds like. It's up to the researcher to determine the aspect of the construct that is being measured by each factor and then to name those factors accordingly. EFA is not without its limitations. It is most important to remember that EFA is driven by the data and not by the theory underlying the data. This means that with the same questions, it is feasible that the best solution yielded by an EFA could change for each sample of participants. Also, the guidelines for making decisions throughout the EFA process are rules of thumb, not strict rules. This is a nice feature because it allows the researcher flexibility to make sure that the final solution makes sense from a theoretical and conceptual perspective, but it's also a limitation because such a subjective process could result in several different correct solutions. It's of utmost importance that the researcher understand the construct of interest and the theoretical relationships around that construct to make good decisions throughout the EFA process. Here are some sources that you might find helpful if you'd like to learn more about the topics introduced in this presentation.